Okay, we've already met two other solid types, the ionics, so this sort of thing here, salt, and the metals. And I did say to you that I want you to describe metals as cations in a sea of valence electrons because it will help you explain the properties of those better. Okay. I also told you that ionic compounds, their formula was a ratio of ions because actually you can't have just one Na with one Cl. Okay, you need lots of them together to make a crystal. What we're going to look at now are the next two, and I'm going to do the covalent networks next. And there are only 3 examples you need to know this year. So there's only 3 examples. If it's not one of these, it's not a covalent network. Although there are variations on them. So the first one is silica, Sio2, which looks a bit like CO2. And you have a molecule on it, but actually it doesn't exist as a molecule. It's a 3-dimensional structure and it's glass. It's actually glass. Okay. The other ones are carbon. They are the different allotropes or structures of carbon. And examiners tend to really like the allotropes of carbon because there are so many. There's the Buckminster something or other ball, I can't remember the second name for it. So the buckyball, which is a C60 sort of thing, but actually technically that's a molecule because there's 60 carbons there. So you need to be aware of that one. It's one that's not a covalent network. There is graphene, which is a single layer of graphite. Now that is technically a 3D network, even though it's only a 2-dimensional structure. There is graphite, which this is representing. You will notice that we've got every carbon, ignore the ones on the edge because this is just a snapshot of a piece of graphite. Each carbon in the middle is bound to 3 other carbons with a covalent bond. Covalent bonds are very strong. These are very hard to break, especially because I've got 3 covalent bonds for each carbon. So it's really hard to rip a carbon atom out of this. If I turn it 90 degrees, these long bars are representing something very similar to what's in a metal. These are representing a sea of valence electrons because carbon's meant to have 4 covalent bonds. But actually, the other electron sits in between the 2 layers. And so it's a sea of valence electrons just like metals have got, which is why graphite is one of the only 3D networks which will conduct electricity, because it has a sea of valence electrons between each sheet of carbons. However, it still has a really high melting and boiling point because of this strong bonding between the carbons. It's hard to rip a carbon atom out of this structure. Okay. Graphite has got some really cool properties. One is that it's an electrical conductor. It's really unusual for a covalent network. It's unique, in fact. Okay. Another really cool one is that it's a lubricant. These layers can slide over each other. They can actually, as a sheet, slide, which allows it to be a lubricant. And that's because the bonding between the layers is very, very weak. The bonding inside the layers is very, very strong. So it's like having sheets of glass to walk on, all on top of each other. They'll just slide over each other. Okay, but the glass itself will probably stay together. Silica, so glass, and diamond have nearly identical structures. That's why they're both transparent, see-through. That's why they're actually really strong. Silica shouldn't be nearly as strong as it is, but because it's a 3D structure, it is. So diamond, and sorry about these metal bars there, the little cube in the middle is just to give it, hold everything in the right shape, because if it gets dropped it shatters. Each carbon has got 4 covalent bonds, so it's just that little bit stronger than this. This is the hardest substance we know of. We don't know of anything that's got the same density and bond strength, so therefore we don't know of anything that's as strong as this. But they have about the same melting and boiling point, because to remove one carbon atom takes about the same amount of effort in both. Okay, so it's really hard to generalise their properties. It's really hard to generalise their properties, but in a nutshell, you need to sort of have a look at diamond and glass. I will say glass rather than silica. Diamond and glass in one group of properties. You should not glasses like, you should not diamonds like. And explaining those versus graphite. and be able to explain those. Now, how would we describe the particles in here? Notice how I've written graphite, or diamond, or graphene. What have I put there? Carbon. So that would infer that these are atoms, because I do the same thing for metals, don't I? I just write Fe. And that's exactly what we say. The particles are atoms. Okay? Now, notice silica Sio2. That's not an SiO2 molecule. It's silicon atoms and it's oxygen atoms in a 1:2 ratio. In a 3D network like that. Okay? The forces inside them are given away in the title. So what sort of forces or bonds are between these atoms? Covalent. Perfect. So covalent bonds are our forces. Okay. So how do we explain things? We talk about the fact that covalent bonds are strong, and we talk about the quantity of them. That there are multiple covalent bonds for each atom, and that will help us explain all the properties of these two and why each sheet of graphite is so strong. Then if we're going to talk about the lubricant and or electrical conductivity properties of graphite, we then talk about the sea of valence electrons between the sheets, which are charged and able to move, or, if we're talking about it being a lubricant, create a weak bond between the two layers. Okay. Any questions on that before I push on to the last one? Yep. So yeah, they're the only three that you need to learn a lot about, because everything else will fall out under those categories. Okay. The lucky last on this one that we're going to do are the molecules. And the reason I leave the molecular solids to last is because we spend a lot of time on molecules, a whole other week at least on molecules. I've made some molecules. Not real ones, of course, just molecular models, to show you what I mean. This is C2H6. It means it's got 2 carbons and 8 hydrogens in one molecule of it. But if I had, and this is called ethane, if I had ethane gas in a container, all of the particles will be that. Well, you know, the real version, not a model of it, but they'll all be 2 carbons bound together by a covalent bond, and each of those bound to 3 hydrogens by a covalent bond. All of them, they'll be identical if it's a pure substance. Here I've got water, H2O, dihydrogen monoxide. Alright? Same thing in pure water, almost all of them will look like that. Water does a funky thing where it dissociates to become OH minus and hydronium, but it'll be like that. The shape's important, and we'll get to that later. And this one here is ammonia. Again, funky shape, that's important later. Okay, NH3. Nitrogen bound to 3 hydrogens. They will all look like that. Well, the real deal. So, those 3 I've actually grabbed need to be taken down to incredibly low temperatures, negative hundreds, basically, negative 100 and something, for them to be solids. What does that tell you about one of the most important properties about molecules? Okay, so that's our explanation. They've got very weak bonds between them. What does it tell us about their melting points and boiling points? Very low, okay? So we have very low melting points, and therefore very low boiling points as well. Okay, because I mean, these are all gases, these 3, at room temperature. Oh, ammonia is touch and go. Can be liquid, can be gas. They are molecules. What charge have I put next to these things? Have I put a charge next to anything there? No. So if they're not charged, what does that tell me about their electrical conduction? If they were solids? No. They don't. Good. Perfect. So electrical insulators. Alright? Those are the key properties, to be honest. Just those 2. They're particles. These are the particles. They're made up of more than one atom. So what do we call things when they're made up of more than one atom? By the way, O2, N2, H2, those are also molecules, molecular solids. So what do we call these little things that are made up of more than one atom? molecules. Okay, so don't get caught into the trap where you want to call them compounds. I've done compounds, more than one type of atom, but a molecule is more than one atom bound together, okay, covalently. So that'll get to that in a minute. So again, the name gives away what the particle is. Lucky last. The bonding inside it is called a covalent bond. That's not what I'm asking about here. What I'm asking is, what holds water molecules next to water molecules in ice? What holds ethane molecules next to ethane molecules in solid ethane? What is going to be the type of force there? And you'll see a whole lot of names given to these. I'm going to write the 3 most common ones there, and they are all allowed to be used in your assessments. I like this one because it's in the name. Intermolecular forces, between molecule forces. It's a nice, easy one. You'll also see them called van der Waals forces. Notice they're forces, not bonds. I want to be very clear on this. They're forces, not bonds. The bonds are inside them and they're covalent. And the last one you might see them being called as London forces or dispersion forces. I'm less keen on these ones, but I'll put it there in case you meet it. So London dispersion forces is the other one. Okay. The top one's actually the best one because there's a subset under this, which is going to be really important for your learning of this stuff next year. So my plea to you is to think of them as intermolecular forces, even if you love these other words that are named after people. This is what they are, the intermolecular forces. Okay, so now we've met all 4 across 2 videos. We've met all 4 particle types, done a very quick summary, and hopefully that'll help you with your homework. Hopefully that'll help you with getting these ideas all together. Any questions before I stop that? Cool.